Let's discuss on the principle behind UV visible spectroscopy. The greater the number of molecules which are capable of absorbing light of a given wavelength, the greater is the extent of light absorption. So there is an important empirical expression that we have been using for that. That is Beer-Lambert's law, which states that absorbance A is equal to log I0 by I, that is equal to epsilon CL for a given wavelength. Log A is the absorbance and I0, that is the intensity of light incident upon sample cell, I, which is the intensity of light leaving sample cell, C is the molar concentration of solute, L is the length of the sample cell in centimeter, and epsilon is the molar absorptivity. So the term log I0 by I is called absorbance and is represented by A. Now, the molar absorptivity or epsilon, that is a property of the molecule undergoing an electronic transition, and it is not the function of the variable parameters involved in preparing a solution. So the size of the absorbing system and the probability that the electronic transition will take place controls the absorptivity, that is epsilon. That ranges from 0 to 10 raised to 6. So the values which are above 10 raised to 4 can be called as high intensity absorption, while values that are below 10 raised to 3 are low intensity absorptions. We can also observe forbidden transitions, that is in the range 0 to 1000. That is a molar absorptivity for a forbidden transition. There is another term that we also have to see, that is transmittance. That is the fraction of the incident radiation transmitted by the absorbing medium. So transmission T is defined as I by I0. So that is the difference between absorbance and transmittance. There are certain terms that are very important when we are discussing UV visible spectroscopy. One important term is chromophores. They are covalently unsaturated groups that are responsible for absorption of UV or visible radiation, and they may or may not impact color to the compound. And the compound which contains the chromophore can also be called as chromogen. So normally chromophores are unsaturated linkages such as C double bond C, N double bond N, because these the pi electrons that are present in this are loosely bound, and they are able to and these loosely bound electrons only require less energy for the electronic transition, and the absorption band occur in near UV region. So if you are saying taking an example of an acetylene that possesses C double bond C and in its structure, and its lambda max is around 175 to 180 nanometer. Another important term is oxochrome. Oxochrome is they are saturated and unsaturated group which consist of one or more pair of non-bonded electron. So oxochromes, we attach them to the chromophore, and that helps it to alter the wavelength by increasing the intensity of absorption and thereby increasing lambda max. So oxochromes are something that we are attaching to chromophores. So oxochromes examples can be OH group, NH2 group, OR, etc. Now we have to see what are some of these shifts that are happening in the case of UV visible spectroscopy. First term is bathochromic shift, or you can say red shift. In this type, absorption maximum shift towards longer wavelength or lower energy. Another term is hypsochromic shift. You can also call it as blue shift. Here, absorption maximum is shifted to a shorter wavelength. So that may be due to the removing conjugation and altering the polarity of the solvent. Third important term is hyperchromic shift. This means there is an increase in the absorption intensity, or Emax or epsilon max is increasing. For example, in the case of pyridine, you can observe the peak around 275 nanometer. Emax is 2750. That is shifting to 262 and Emax around 3560. The change is happening when pyridine is replaced by methyl pyridine. So in pyridine to methyl pyridine, there is a presence of CH3 group there. So addition of these kind of auxochromes increases the intensity of absorption. And the last term is hypochromic shift. This means there is a decrease in the intensity of absorption or a decrease in the extinction coefficient. So hypochromic effect is caused by the insertion of group which changes the geometry of the molecule. That is hypochromic effect or shift. So these are the four different terms. Bathochromic shift, that is red shift, a shift to longer lambda or lower energy. Hypsochromic shift is blue shift, shift to shorter lambda or higher energy. Hyperchromic effect, an increase in intensity. Hypochromic effect, a decrease in intensity. So this is a plot. Hyperchromic, hypochromic, bathochromic shift. That is the wavelength is this side. So wavelength is increasing, bathochromic, wavelength is decreasing, hypsochromic. Epsilon value is it increasing, it's hyperchromic, and epsilon value decreasing, it is hypochromic. Now let's also discuss about some of the applications of UV visible spectroscopy. First one is the detection of impurities. So UV visible spectroscopy is one of the most important methods for the determination of impurities in organic molecules, because additional peaks can be observed due to the impurities in the sample, and it can be compared with that of the standard raw material. And another important application is the structural elucidation of organic compounds. So it is UV visible spectroscopy can be used for the structural elucidation of organic molecules, such as in detecting the presence or absence of unsaturation, the presence of heteroatoms, like that. So these are some of the applications of UV visible spectroscopy.